So a nerve fiber from a mammal has a surface area of this, and the ion concentration are under physiological steady state conditions as indicated below. The temperature is 300 Kelvin. And when the cell is at rest, the membrane potential is given at minus 18 millivolts. An experiment has found that the passive net flux across the cell membrane for sodium is given at this value. So the first thing they want you to do is, what is the passive net flux across the cell membrane for potassium and which direction does it occur? Right. They've given you the passive net flux across the cell membrane for sodium, right? And since they're talking about physiological steady state, right, and they even give us the membrane potential at rest, which is minus 80 millivolts, well, then we would automatically assume that the sodium-potassium pump is working, right? The pump that is pumping 3 sodium ions out and 2 potassium ions in, right? This is the pump that is working on the physiological steady state, all right? They've given you the passive net flux for sodium, but what is the passive net flux for potassium? And remember, the difference is, you're pumping 3 sodiums out, 2 potassiums in, right? And so you can actually just take the passive net flux across the cell membrane for sodium, which is this value, and multiply it by 2 over 3. This will give you the passive net flux across the cell membrane to being this value, and the passive flux of potassium will go out of the cell, right, eventually, because you'll go from high to low concentration, right, as opposed to the sodium potassium pump pumping K plus into the cell, right? So then it will go out. When you pump it in, then it will go out. Now they want you to calculate the power, so work per second the sodium potassium ATPases in a single cell provides during the active transport of sodium. Okay. Again, we're talking about the sodium potassium pump working here at steady state. And they want you to calculate the power in sodium potassium ATPs in a single cell provided during the active transport of sodium. We utilize the electrochemical potential difference because we assume it's talking about active transport. The gas constant is given, Faraday's constant is given, the temperature is given, intracellular, extracellular concentration is given, ion valence for sodium is of course 1, Faraday's constant given, membrane potential is minus 80 millivolts. We put it into the equation, we calculate the electrochemical potential difference for sodium. And now we know how much energy it takes to move 1 mole actively, right? This is the value. Now we need to find out how many moles are being moved. And we can simply do that by taking the flux surface area, so this surface area, and multiply it with the passive net flux for sodium. And this will give you the amount of moles that need to be moved in 1 second. Right? Now, if you multiply this value with the electrochemical potential difference, it will actually give you the power. Right? So the sodium potassium ATPase provides a power of 6 times 10 to the power of minus 13 joules per second. Of course, it is the numerical value. The power cannot be negative. Now we need to calculate the power the sodium potassium ATPase in single cell provided during the active transport of potassium. Before we talked about sodium. Now they want us to do it for potassium. So we will still use the electrochemical potential difference. Now we'll use it for potassium right here. So here we have the gas constant, the temperature, intracellular concentration for potassium, extracellular concentration for potassium. The ion valence still 1. Faraday's constant, nothing has changed, and the membrane potential has not changed. Now similarly, we need to find out how many moles are being moved, right? And this is different, right? Because although the surface area of the flux is the same, the flux itself is different. But we've just calculated the flux of potassium, or the passive net flux, to being this value. And so finally, adding or multiplying these two together, can give us the amount of moles being moved in a second, right? Now this multiplied by this will give you the final work. So the sodium potassium ATPase provides a power of 6 times 10 to the power of minus 14 joules per second, right? So this is for potassium.